All right, so this talk will be a little bit technical, and it's about some basic research that we have started in my group that I'm really, really excited about. And it tries to address some of the challenges that we see with current machine learning. So let's get moving. So what's deep learning about? Deep learning is about representations. It's about how we can transform, say, sensory data into a form that's more abstract, such that in those new spaces of representation, the computers, or brains for that matter, can take better decision, can better understand the world, can control the world, and so on. And one of the things that I had been thinking about for a long time is it'd be nice if the variables in that high-level representation could actually correspond to the kinds of variables that we manipulate with language, we humans. And typically those variables are what we call causal variables. In other words, they're the kinds of things that you can consider either a cause or an effect of something else, sometimes both. But up to now, I don't think we had a good way of building systems that can discover causal variables. So this is one thread, motivation for what I'll be telling you about. From the beginning, the question we were asking was, how do we transform the data into this new space of representation where the variables corresponding to the underlying causes are separated from each other, are disentangled? That's the term that I introduced a long time ago. And in addition to separating those variables, of course, we want to find the relationships they have to each other, like which is cause of which, and what kind of effect does a variable have on another one. These are some of the fundamental questions that scientists are trying to answer when they try to understand the world. But these are also the kinds of questions that we would like an AI to figure out by themselves, right? And what I'll be arguing today is that this question is related to one that seems very different that we've been asking in machine learning, which is how do we represent knowledge in a way, knowledge that the learner is acquiring from the data, in a way to separate it into pieces that can be easily reused, right? So there's a notion of modularization. For a few years, researchers in deep learning have been asking how to separate the neural net into modules that can be dynamically recombined in new ways when we consider, for example, new settings, changes in distribution, or new tasks. So this is related to another important notion in machine learning called transfer learning. That is, how do we build learning systems that not only work well on the training data, but then can adapt quickly on new data that comes from a related distribution, so that you don't need tons and tons of data for this new setting in order to do a good job. And we can have systems that are robust when the world changes, because there are non-stationarities. The world changes all the time due to interventions of agents, due to our incomplete knowledge as we move around in the world, and so on. Okay, so that was a bit of a long introduction, but I think it's important to understand the motivations for this. Now, in classical machine learning, the learning theory is based on the idea that we only thinking about one distribution, the training distribution, and we're going to sample training data, we're going to sample some test data from the same distribution. But once you start thinking about the scenario where things change in the world, the distribution changes, this whole theory is not sufficient anymore. And maybe that explains a lot of the issues that companies have when deploying machine learning products. When, say, you train on data from one country and then you test, you apply the system in a different country, or, for example, maybe people with a different distribution of genders or races, as we've seen recently, and things don't work as well. So that sort of robustness is something that current learning theory doesn't really handle, because it's about how we generalize from data from the same distribution as the training data. But it doesn't tell us anything about how to generalize to new distributions that, of course, must have some relationship to the old distribution, otherwise we can't say anything. But still, we'd like to be able to handle those changes that happen in the world, which we call non-stationarities. And I'm hoping this will also, this kind of investigation that I'm talking about will also help us build models of the world that are better, that have more common sense than current machine learning. If you look at the kinds of mistakes that current systems make, you realize that they don't really understand the world around us. Even a 2-year-old understands things like physics, of course, in an intuitive way, much better than current AI systems. And even a 2-year-old understands human psychology and social interactions better than current AI systems. So it looks like we're maybe missing some fundamental ingredients. I don't think, for that matter, that we have arrived with all the progress we've made and that has been celebrated recently. There's a lot more basic research that needs to be done. Right. And when we ask the questions, how do we make our current systems better models of the world? One of the ingredients that come up, to my mind at least, that we don't really master well is causality. So I mentioned causal variables earlier, but current machine learning systems, even those that try to model the distribution, don't really explicitly try to deal with this notion of causality. And if you think about, if you do a little bit of introspection about yourself and you're trying to observe your own thoughts, which is a good exercise, by the way, you'll notice that very often your mind is focusing on trying to explain what is being observed, right? Trying to find the causes of what you've seen. But this is not something that we're currently doing actively with our current research. But I think will be important to build good models of the world. Okay, let me skip that. Now I'm going to propose a hypothesis to help us deal with how distributions of the data change. And that hypothesis is inspired by work by Bernard Shopkoff and collaborators who wrote a great book recently on causality. And that hypothesis is that the changes in distribution are small if you represent the information about the distribution in the right space, in the right way, right? So like in the space of pixels, it may look like things change a lot. For example, if I shut my eyes, pixel-wise, things have changed a lot. But really, it's just one little thing in the world that changed. My eyes got closed. So we don't want to model the world in the space of pixels. We'd like to model in this space of causal variables. And the hypothesis is that in that space of representation of the structure between the relationship between those variables, the changes will be small. In fact, we'll be focused on maybe just one variable. So for example, if I act in the world, if I do something like I move this around, I am only changing one thing at a time in the world. Well, one thing in the right space of representation, in the space of these causal variables. So like this object is something I want to model at the high level. But the pixels, it's not something I can act upon easily. And so it's not the right space to do that. But so this idea that in the right space of representation, the non-stationarities involve changing just a few of these mechanisms that relate variables to each other is what we're going to be writing on. And in this research, we are going to try to take advantage of this hypothesis to build systems that can adapt quickly to changes in the environment and in fact learn about causality. So let me see how we can do that. Well, if we have represented our knowledge in this space of causal variables, then this hypothesis of small change should mean that I can recover from that change, adapt to that change with very little data, right? Because if just a few things change in my representation of the world, for example, I'm representing those objects, right? And only one of them changed. I only need to gather data about that change, and I don't need a lot of examples. So that's what we call sample complexity in the jargon of machine learning. So now, the idea is that we can turn this upside down and say, well, if having the right representation of knowledge leads to fast adaptation under that hypothesis, then we can use fast adaptation as a training objective to find a good representation of knowledge. This is the heart of what we're trying to do. And we're going to be studying this for now in a very simple toy scenarios. I like to do these kinds of very small, easy to understand experiments where we really control things and we can understand what we're doing. So the simplest possible example of this idea is to try to figure out, given two variables A and B and observations of the pair A and B, which one is cause and which one is effect. So for doing this, we're going to assume that the distribution between those variables is going to change because of an intervention. So some agent is acting on one of those variables. And the claim that I made just earlier, that we can adapt faster in this setting, comes down to the following, that's what's represented in the equation here, that if we represent the joint distribution as the product of two modules, one which captures the probability of A and the other that captures the probability of B given A, and each of these modules have their own parameters, but only one of the two modules is going to change when the distribution changes. For example, P of A changes. Then the error, the gradient, that will be measured on the modules which didn't change, like P of B given A, will be 0, right? It's sort of almost obvious. And so it means that the modules which didn't change after the change in distribution don't need to be adapted, and you only need to adapt the ones that changed. And that's why we're going to observe faster adaptation. So, so this, I believe, is related to important issues with neural nets currently. So one of the things people have observed a long time ago is called catastrophic forgetting, and difficulties when neural nets are trained on one task and then another one and then another one in sequence, and they sort of forget the old ones and need to almost relearn from scratch the new ones, which apparently is not at all what humans are doing. We are able to reuse the past knowledge even though the tasks we are seeing, the examples we are seeing, come in sequence. And I believe that this is due to the fact that in current neural net architectures, it's like if every parameter wants to participate in every job, in every part of the knowledge representation. And so when something changes in the world, like one of these modules changes in a ground truth model of the world, all of the parameters, all of the weights of the neural net want to change. And because there are many of them, it takes a lot of time, a lot of data to adapt all of them to adapt to the change. But if we were able to factorize the knowledge, if we were able to break the neural net into modules that specialize on these different causal relationships, then we might be able to have much faster adaptation. So we verified this empirically in this very, very simple setting that I talked about, where you only have these two variables, A and B, and the learner doesn't know whether A is the cause of B or B is the cause of A, but it's trying to figure out which is which. And so we consider two hypotheses, one where the learner assumes that the correct answer is A is the cause of B, and that's in blue, and the other where B is the cause of A, that's in red. And we're just seeing how fast the learner adapts to a change when the distribution of A, the cause, has changed from one distribution to the next. And now we're looking on the second distribution after the change, how fast the accuracy, this is actually the log likelihood of the data, improves as the learner adapts to the change in distribution. And what we see is that under the model that has the correct causal direction, the adaptation is much faster than under the model that has the wrong causal direction, right? So in other words, if I have in my head the right causal model, I can adapt faster to changes in the world. So this is, of course, a toy experiment, but this is what it's trying to validate. And now what we're trying to do is say, well, if a good causal model leads to fast adaptation, maybe we can use fast adaptation as a training objective to find good causal model. So this is what we do. And so instead of thinking of the change in distribution, non-stationarity, and so on, as a hindrance, like as we usually think about in machine learning, we don't have enough data for this new domain, or there are too many parameters to adapt compared to the amount of data we have, or the agent in some environment faces continuous changes that it's difficult to track. We think of all these things as a source of signal, a source of information that can help the learner figure out the causal structure, which is something fundamental about how the world works, right? Okay, so we run experiments with this scenario that I've been talking about, where we consider a sequence of two distributions, where the second one is obtained by modifying the first one on one of the variables, say the cause. And ideally, what we would like now is to use these training signal to figure out two things. One is really fundamental in deep learning, which is what we call the encoder. How do we map the observed data, which are not causal variables, which are like pixels, to the causal variables? In other words, it's a transformation that goes from pixels to, say, objects, right? And then what is the relationship between those variables? Which one is cause, which one is effect? And so we're going to use what's called meta-learning for learning these things. So the idea of meta-learning is we have two types of learning embedded in each other. So we have like the normal learning, where the learner adapts to the examples as they come and modifies its parameters. But then sort of an outer loop at a slower pace, we're learning something more generic that's true across all of those distributions, all of those changes. And these are what we call meta-parameters that are being adapted at a slower pace, whereas for each change in distribution, we have these fast adaptation of the regular parameters, right? And so the meta-parameters are those things about the world which we consider to be true across all of the changes in distribution that we'll be observing. Okay, so I don't have a lot of time left, but we run these experiments, and I'm sorry if the equations here didn't come out right, where we consider these two hypotheses I talked about. I'm not going to go through the math, but we define an objective function that is this meta-learning objective corresponding to how fast the learner adapts. We showed some theory about if we do gradient descent on this objective, this meta-learning objective, then the learner can actually recover, in this very simple case with two hypotheses, the correct answer of which is cause and which is effect. And we verified that indeed doing this meta-learning allows the learner to figure out cause and effect, and we can measure how fast it converges across episodes. Now each episode corresponds to seeing one more change in distribution. So the agent goes, you can think of it, agents go through the world and things change from one episode to the next. And we can see how fast now at the level of these episodes, like these meta examples, the learner figures out the correct causal direction in this case. So we've done a lot of experiments playing with this, with different kinds of relationships between the variables, linear, nonlinear, unimodal, multimodal. I'm not going to go through these things. We've played with a very simple version of the system where the learner has to discover this encoder, but here it's very simple linear transformation that relates the observed variable to the true causal variables, and it can recover those things. And currently what we're doing is extending this work, which was with only two variables, to more variables. And so we have slightly modified the math to be able to handle the situation with more variables. So we are experimenting with, again, neural nets, but now those neural nets represent the conditional distribution of one variable given all the others or a subset of the others. And what we learn is which subset, so that's the connectivity of the graph, right? So for example, we can learn these graphs here with 3 variables where instead of having everything connected to everything, we learn the right pattern of causal dependency. So with that, I'm going to stop and thank my collaborators on this project, Tristan Deleu, Nassim Rahman, Rosemary Kay, Alexa Belyaniuk, Anirudh Goyal, Chris Paul, and Rémi Leprial. Thank you.
So thank you very much, Yoshua. Well, we're going to have a little bit of Q&A, but let me throw the first one at you. So I was just talking to a group of chief data officers from Global 2000 companies, and I asked them, so should we be paying attention to meta-learning? And they basically told me, this is science fiction, but then again, 5 years ago, we would have said the same thing about deep learning. So given what you've just said, what is possible for companies, for governments, and for others, and how quickly should the implementers of AI in the world start paying attention to the research that you just talked about?
Well, some companies are paying attention. As you know, I'm a co-founder of Element AI. And from the beginning, one of the focus of the research group has been transfer learning. And meta-learning is one of the key tools for that. So the reason I think companies want to pay attention to this is very often in practice, you're dealing with situations where you have a new scenario where you don't have enough data, right? And so standard techniques will just not generalize very well. But you might have data accumulated from other settings, and if you can take advantage of that to have very fast adaptation, a good transfer to the new setting, it can have a lot of practical value.
Wonderful. So let us go to our first question here in the audience. Richard.
Yes, so the question is that, I have a couple questions. One is about counterfactuals.
Yes.
And the other one is really about using analogy for transfer learning. So those are kind of like an old work type of stuff, right? A lot of stuff that Judea Pearl and Forward, they have worked on. And how do you think those things will be related to the work that you are doing here?
So I'm, extremely grateful for the work that people like Judea Pearl and others have done. And it has really inspired me a lot. What's missing from the kind of work they've done, from the point of view of deep learning, is how do we figure out what those causal variables are? So the typical applications that Pearl and company have looked at is in typical science, like in medicine or astronomy or whatever. The scientist defines what the variables are, and the observations are directly of the values of these variables. But if you're a robot, or if you are an AI, or if you're a system working in a world where we don't know what the right variables are, we'd like to have something like deep learning figure out the right representation. This is what deep learning is about. So that's really what I'm after. That's new.
Next question, right there. A microphone is coming.
My question is that when you were saying about deep learning and its applications and the meta-learning, we have also learned about adversarial learning and all that stuff. But do you think it has some connection with the creativity?
With what?
The creativity, people's creativity.
Yes.
When babies, the analogy you have shown.
Absolutely.
Yeah, so they know about, they are aware of their environment.
Yes.
But what about when they build something out of nowhere?
Right. So we've already made a lot of progress with deep generative models like GANs in producing, like having computers generate new images, so they're creative, but right now they're creative in the pixel space. What we really want is to have machines that are creative in this abstract space that I've been talking about that would like machines to discover. If you do a bit of introspection about your own imagination, your own creativity, you're projecting yourself into the future or in the past, or thinking of new things. It's not in the sensory level, it's in this abstract space of high-level variables that you're sort of gluing together to build something new. So we have the technology to build new things at the pixel level, and now we have to extend it to the ability to build new things in this high level of abstraction where we don't necessarily build an explanation for everything, but just about a few elements that you're consciously aware of at a particular moment.
Next one. I can't see if there is one. So I have one last one for you. So what you just spoke about is something that I don't think has made its way out to the corners beyond academia, which is that we think of AI as a prediction machine, but there are a lot of really cool generative approaches. What does that make possible that you couldn't do before using traditional supervised learning?
Well, many things. Humans are very good at imagining, right? And so right now, GANs are already being used to synthesize images, but actually they're being used to synthesize things like molecules. So we have research on synthesizing new materials, new drugs. You could imagine there's work in synthesizing text, right? So you could use that as a tool for generating text conditioned on some context. I think the possibilities are immense of using these creative tools in many new ways.
Well, thank you very much. Can we get a hand for Yoshua? Very good.